Welcome back. We have been talking about the design of the introductory programming course. We discussed it at the level of outcomes and topics, and now we are filling in some details. So now we are going to look at exactly what we expect to be taught when we talk about programming or writing programs. So writing programs is really the focus or the centroid of the course, and so what exactly do we want here? So students must somehow or the other, not explicitly as such, but in any time you talk about programs, you should talk about this standard strategy. What is the standard strategy? Understand the problem. Okay. So understand the problem, we said, means devising input instances and corresponding output values. So what output value is needed for what input? So at this level the students must understand the problem. They must be able to figure this out on their own. Then they should figure out how to solve it manually. Don't even get to a computer unless you know how to solve the problem manually. So for this, they may need to collect some information about the problem domain. So is the problem about numbers, about digits of a number, about physics, whatever it is, the student has to maybe shift gears a little and go into a mode in which he or she tries to remember what he or she has learned about these topics. Okay. So then the student has to make a plan. Now here in general it might mean something like break up the task or try to satisfy constraints gradually, but more often it might mean that the student already knows how to solve the problem manually, or it's a relatively simple thing. In this course we are not expecting students to invent very sophisticated algorithms, so the student will probably do this step fairly fast. Okay. Maybe trying some standard strategies such as try all possibilities. Okay. But what the student has to say is, what are you going to compute at intermediate steps? So just as for the problem of calculating the value of E, we said that in the iteration we are going to calculate, in the ith iteration we are going to calculate 1 over I factorial. So when I say make a plan over here, I really mean this. Describe what you are going to do in your iterations and write it down. Okay. So formulate an invariant that you would like your code to satisfy, and only then try to write the code. Okay. So execute the plan, which means write the code. Review the program and see if it can be improved. Yes. Okay. Okay. So that is what I want to say about writing programs. We will have a lot more discussion of this when we discuss pedagogy. Data structures and standard library. So the motto here is understand pointers but avoid using them. Okay. Low level features are very error prone, and hence this warning. So vector class from C++ standard library should be taught, in my opinion. So it is a class which is almost core. I would say it is really core. But of course you can do without it. C programmers do without it. But it is such a great class that such an easy class to use as well, that you really should consider it core. So it's an extensible array, useful in most situations, not only where arrays are needed, but even linked lists may be used in C. And you get it for free essentially. You don't have to write any code to implement a vector. It is far safer and much more efficient than linked lists. It is templatized on type, so which means it works for all types. It does memory management on its own. It's not visible to you. So you get something really clean and elegant. String class from the C++ library is similar. Okay. It is far convenient and safe as compared to null-terminated strings of C. And it allows you to have this mental image that strings are just like ints. They may be long, but they're there. They're there in your, I mean, it doesn't really hurt if you think of the strings as residing in your activation frame. They actually don't reside in the activation frame, but you can think of them as residing in your activation frames, just as you can think of ints as residing in your activation frames. Maps, sets and containers are other powerful data structures from the standard library, but those are tier 2 core. And they are actually very powerful. They have this notion of iterators, which enable you to navigate through data structures very conveniently. And they are discussed, all of these are discussed in chapter 22 of our textbook. Compiling, testing and debugging programs is an important skill. It's frustrating and therefore very important to assure your students that it is something that everybody does, and everybody does comfortably well with practice. Okay, first of all, encourage students to use text editors which will indent code. If your code is not indented, it is very hard to spot mistakes. Okay, you may think that a block is ending at a certain place, whereas it ends at a different place, and therefore no wonder your code is doing something wrong. Okay? And your editor may not immediately have the indentation feature. A plugin might be needed. So what you should do as a teacher is to get information about this and tell your students that, look, if you are using this editor, this plugin is there, and use it. You should encourage students to create test cases before writing code. A part of the reason is that students should understand the specifications first, and that they create test cases is a proof that they have understood the specifications. It is shocking that even experienced programmers might start writing code before they fully appreciate all the intricacies of the of the specifications that are given to them. Okay? And test cases should be stored in input files which can be read by input redirection. So you should teach input-output redirection somewhat early on. Encourage students to put plans as comments in code because they will help in debugging. Okay? And of course, it will mean that they first of all have a plan in place. Okay? Teach about assertions. Now, many students do not realize they can liberally put print statements which will help in debugging. It is obvious, but they don't realize, so tell them. Analysis of running time is, in my opinion, tier 2 core, but AICTE says it is core, so let's talk about it a little. So simple operations require one step. That is basically the guiding principle. Arithmetic operations require one step. Well, they don't all require the same amount of time, and so not one step, but for practical purposes of this course, it is convenient to think of them as one step. Similarly, storing a value into a basic type variable, int, double, float, takes one step. Okay. So a corollary of this is that the time for assigning to a structure variable is proportional to the size of the structure. Dereferencing a pointer takes constant time, indexing into an array takes constant time or one step, think of it as one step. Okay. So the second idea in analyzing running time is often not to worry about every operation, but just worry about the important operations. So if you are evaluating a series, you may be asking, look, how many multiplications am I doing? Because those are the dominant operations, or multiplications or divisions, whatever. Okay? So you might say that the number of operations is proportional to n squared if you evaluate each term separately. Or it might be that they are proportional to n if we evaluate the ith term using the I minus 1th. So I would recommend that when you teach how to evaluate E, you do a quick calculation to tell students how many divisions they did or multiplications or whatever. And don't really dwell on this too carefully. You should say that proportional to n squared can be written as a short form as O of n, but again O of n has a formal meaning. It is too early to talk about the formal meaning. Okay? So proportional to n can be written as O of n, proportional to n squared can be written as O of n squared. Don't talk about the formal meaning. So this is basically the extent to which running time should be analyzed in this course. And the discussion may happen while talking about specific algorithms. You probably don't need to devote a lecture to this or anything. So finally, how do we inculcate belief, or exactly what are we hoping to accomplish? So we want to persuade students that computers can solve problems in all fields. So we have to give good examples for it. Okay. We don't need to give details. We just have to sound right, or we should, I mean, it should be that, look, students will think that, oh, this seems reasonable. We have to sound reasonable. Okay. So text processing, searching, if we want to say that computers can do it, then we can say that, look, text is represented as a sequence of numeric codes. So now if you want to search, we are searching through numbers, we are comparing numbers, and therefore students can believe that, oh yes, text processing or text searching can be done. So search is finding patterns. Image processing, the image is discretized and represented as a sequence of numbers. So again, recognizing things are like finding patterns. Okay? A more complicated example is weather prediction. How does that happen? Now this is a subject in itself. We can't explain all of that. But I feel we should explain something. Here is what we should explain. So we should say that to do weather prediction, we are going to set up a system of equations, and our unknowns will be pressure, temperature, humidity, whatever, at different points or times on the surface of the earth, and we will relate them using laws of physics. So if we know the initial conditions, we will be able to calculate the values for subsequent time steps. This is about it. We cannot say what laws we are going to use, because those laws are a science by themselves. But we should state at least this much. So this is going to persuade the student, yes, weather could be predicted. Okay? And that is going to improve his respect for our subject. Okay, so we set up the subject, we set up the systems, we solve the system. So then we should do a detailed discussion of an easier but important computation. So we cannot talk about weather, it is too complicated. But we can, and we should talk about simpler physical systems. So for example, gravitational simulation. Everybody knows Newton's law of gravitation, everybody knows Newton's laws of motion, and using those, we can in fact predict reasonably well how, say, planets in a solar system move. And that calculation is one of the classical calculations that people do. Astronomers do this calculation all the time. And we can describe it, we can get students to program it. This is something that will increase their belief in the utility of computers. And this is discussed in chapter 19. To inculcate belief, we should assign programming problems from many areas as possible. Math, finding roots, calculating math functions, physics, kinematic calculations, gravitational calculations, which we just said, tax calculations, okay. Games can be programmed, graphics and pictures. So computers are good with numbers, but students should be persuaded that computers are also good with pictures and animations. Okay. This will need some additional code, what is called scaffolding code, and we should provide it. Okay. The more areas we can bring in, the stronger will be the belief. We should provide domain knowledge whenever it is needed. So if we say write a program that prints the number obtained by reversing the digits of a given number, so we need domain knowledge how to manipulate digits. So for example, students need to know that x mod 10 gives the least significant digit, or x divided by 10 gives the number obtained by removing these significant digits. X times 10 shifts the digits of a number to the left. Okay? And if I want to get the number, the value of the number itself, I can use this formula to calculate it given the digits. Now, these facts are expected to be known by students. After all, they are taught maybe in primary school, but students may have some difficulty. So, remind them, be nice to them and remind them. Okay? In general, if we want our students to write programs for solving a problem in domain X, we should revise the basic facts, principles, formulae of domain X very quickly. We don't have to teach them, we just have to remind them. Okay? Revision could happen in class while solving another problem from that domain, or by giving a set of printed notes. Okay, so we now come to the conclusion of this sequence of lectures. So I want to summarize. So what is our approach about? So first, we are going to stress manual computation. Manual computation is important. Students should first find a manual algorithm before finding a computer algorithm or before writing a computer program. Problem solving strategies learned by the students through school should usually be adequate for inventing the manual algorithm. We are not going to teach problem solving strategies. We might just do some fairly simple common sense things, but elaborate problem solving strategies, there is no time in this course. Now, what we do teach is teach strategies for translating from manual algorithms to computer programs. Okay? Then we are going to encourage students to use and master simple language constructs. We will teach some clever algorithms to build excitement. Okay? We will take programming problems from many areas. Okay? We consider areas that our students have studied, okay, and want to study, which are consistent with their career goals. Okay. We are going to revise the relevant facts. We gave a detailed list of topics that we are going to cover in our syllabus. We also talked about what exactly we meant and what exactly we intended to teach for those topics. So, in the next lectures, we are going to talk about pedagogy, how exactly we will do the teaching. Okay? Yes, we also talked about compiling, testing, debugging. This can be frustrating, and so we should handhold as much as possible. So, final remarks regarding students: we should not despair about their capabilities. Students will perform if we can motivate them as per their maturity, taste and career goals. You should remember that the syllabus is a compromise between what you would like to teach, what students would like or can handle, and what will be possible in the given time and resource. So, we need to iterate over it. So, these are the references, and there is more. I won't go through the references, but we'll stop over here. In the next lecture, we'll talk about how to teach all of this, or the pedagogy of the course. Thank you.